You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your Cloud Plus certification journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. At the foundation of every cloud environment are low-level network components that support the operation of higher services. These elements often include name resolution systems, virtual network segmentation, overlay technologies, proxy settings, packet size configurations, traffic shaping rules, and time synchronization protocols. When any one of these components fails or behaves inconsistently, the result can be misleading and difficult to diagnose. A service may appear online but not respond correctly. Latency may increase without any visible cause. Applications may break in unexpected ways. In this episode, we walk through how to troubleshoot these lower-level but essential systems when performance or availability is affected. The Cloud Plus exam includes coverage of network support technologies and related configuration dependencies. Candidates are expected to recognize and diagnose issues related to domain name system failures, virtual network tagging, proxy misbehavior, packet fragmentation, traffic prioritization, and time-related service faults. You may encounter questions about mismatched maximum transmission unit values, dropped packets in overlay networks, or name resolution inconsistencies in private zones. Being able to work beneath the application layer and isolate failures in DNS, VLAN overlays, or time services is essential for modern cloud troubleshooting. DNS resolution is one of the most critical dependencies in a cloud environment. If name resolution fails, applications will be unable to connect to internal services or external APIs. Common indicators of failure include services failing to start, commands that hang when trying to access remote systems, and logs showing unresolved host errors. Tools such as NSLookup and dig can be used to manually test whether names resolve successfully and to view time to live values. System logs may also show DNS query failures or fallback behavior. Candidates must confirm that DNS settings are configured correctly at the operating system, cloud VPC, and application resolver level. Even when DNS settings are correct, propagation delays and conflicts can cause unexpected behavior. For example, when a new DNS record is created, clients may not see it immediately due to cached results. Similarly, records with the same name in both private and public zones can compete, resulting in unintended resolution outcomes. These issues often cause intermittent service failures or incorrect routing. Administrators should reduce time-to-live values on dynamic records and verify resolution paths across zones. Testing with multiple resolver paths helps confirm whether the intended record is being used. VLAN and VXLAN tagging allows cloud networks to isolate traffic into segments, often for security, performance, or multi-tenant management. However, incorrect tagging causes packets to be dropped or misrouted. If the tag on a frame does not match what the switch or virtual network expects, the traffic may never reach its target. Misconfigured VLANIDs or VXLAN segments that do not align across hosts lead to broken communication. Packet captures help identify whether traffic is tagged as expected or being rejected at the switching layer. Confirming tag consistency across hypervisors is essential for maintaining segmentation. Overlay networks abstract Layer 2 communication over Layer 3 infrastructure, allowing cloud services to simulate local connectivity across distributed systems. Technologies like VXLAN enable this by encapsulating Ethernet frames inside IP packets. When overlays are misconfigured, entire services can become unreachable, even when the underlying infrastructure appears healthy. Common failures include incorrect route advertisement for tunnel endpoints, mismatched MTU settings, or unsupported versions of overlay agents. Cloud administrators must ensure that the overlay configuration matches across all nodes and that cloud-native overlay systems align with the host's network stack. Proxy servers are often used to manage outbound access from cloud workloads, applying filtering, caching, or access control rules. Misconfigured proxies can silently block service calls, redirect traffic incorrectly, or cause authentication errors. Environment variables such as HTTP/PROXY and NOPROXY are used by many applications and operating systems to determine when and how to use proxy services. If these values are incorrect, the application may route traffic to an unavailable service or bypass security requirements. Troubleshooting involves reviewing proxy configuration in both environment settings and application logs and testing connectivity with tools such as curl or WGET. MTU mismatches can lead to packet fragmentation or outright packet loss. The MTU determines the maximum size of a packet that can traverse the network without being broken up. When one segment of the network allows larger packets than another, oversized packets may be dropped or delayed. This often manifests as failed uploads, slow API calls, or random disconnects under load. Tools like ping with the do not fragment flag or traceroute with MTU options can detect these issues. Administrators can resolve this by reducing MTU sizes or ensuring that intermediate devices support the expected packet size. Quality of service policies prioritize traffic types to manage congestion or meet service levels. However, if QoS tagging is applied incorrectly, high-priority traffic such as voice or video may be delayed or dropped. Traffic shaping systems use DSCP tags or similar fields to assign priority levels, and misalignment can cause class-based queuing to malfunction. This results in jitter, poor call quality, or delayed service responses. Monitoring queues and inspecting tags with packet capture tools helps verify that QoS assignments are functioning as intended and that critical services are not being misclassified or throttled. Time synchronization is critical for many services, especially those that depend on time-based authentication, scheduling, or logging. If clocks drift between systems, log entries may become impossible to correlate, scheduled jobs may fail, or token-based security may break. Using network time protocol clients such as NTPQ or ChroniaKey allows cloud administrators to verify synchronization status and confirm that each node is using an accurate and consistent time source. Even small differences of a few seconds can cause widespread issues in cloud environments where security tokens and event timestamps are used extensively. Cloud-native environments often involve multiple layers of abstraction, making it difficult to determine where a failure is occurring. Underlay failures relate to the physical network infrastructure, such as switches or routers. Overlay failures involve virtualized constructs such as VXLAN tunnels or encapsulated traffic. Tools like flow logs, virtual private cloud mirrors, and packet tracing systems help isolate whether the failure is due to a physical link or a virtual construct. Knowing where to focus attention saves time and ensures that troubleshooting efforts are applied at the correct layer of the network. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Monitoring DNS requires a combination of internal and external validation. Public resolvers such as those offered by major DNS providers can confirm whether a domain is globally accessible, while internal resolvers verify that private names resolve correctly within the cloud environment. Synthetic checks simulate DNS queries from multiple points and alert when responses are delayed, incorrect, or missing altogether. These checks are useful for detecting latency problems, stale cache entries, or records that return negative responses like NX domain. Monitoring tools should be configured to detect shifts in TTL values or unexpected changes to canonical name mappings, both of which can cause resolution to behave differently than intended. Reverse DNS, also known as pointer record resolution, is another area that can create operational challenges. Many services, including logging platforms and certain email filters, rely on pointer records to verify that an IP address maps back to a valid domain name. If these records are missing, misconfigured, or outdated, services may reject incoming requests or record traffic incorrectly. Administrators must ensure that reverse lookup zones are properly delegated and that entries are synchronized with forward records. Tools like dig with the reverse flag can confirm whether pointer records resolve and whether the return domain is appropriate for the IP in question. Trunking misconfigurations in VLAN or VXLAN environments can block traffic at the switching layer. Trunk ports are configured to carry tagged traffic from multiple VLANs across a shared link, and if the allowed VLAN list does not include the segment in question, those packets will be dropped. This causes connectivity problems that are difficult to detect at the application layer. Cloud administrators must validate that switch and hypervisor ports permit the necessary VLANs and that tagging is consistent throughout the path. Packet captures at the host or switch edge can confirm whether tagged traffic is being carried or discarded during transmission. Proxy auto-configuration mechanisms may interfere with expected traffic flow, especially when environment variables or pack files override default behavior. If a proxy is automatically selected for traffic that should have been routed directly, service calls may fail without an obvious error. Logs may reveal redirection attempts or authentication challenges that indicate proxy interference. Disabling proxy auto-detection or adjusting the rule set to exclude certain domains allows for better control. Testing tools and verbose request logging can validate whether a proxy is being used, even when it is not explicitly configured by the administrator. Maximum transmission unit settings must be consistent across the entire network path to prevent fragmentation or dropped packets. Devices such as firewalls, VPN gateways, and tunnel endpoints must all support a uniform MTU or negotiate properly to avoid incompatibility. Mismatched MTU values often cause large data transfers to fail or appear to hang. VPN and overlay systems are especially sensitive to MTU discrepancies, as encapsulation increases packet size. Logs may show ICMP fragmentation-required messages or silent drops. Cloud professionals should monitor path MTU discovery and validate negotiated values when troubleshooting payload delivery failures. Quality of service issues may go undetected until performance-sensitive traffic begins to fail. When voice, video, or critical control traffic is delayed or dropped, the cause may be incorrect DSCP tagging or an imbalanced class-based queue configuration. Packet captures can reveal how traffic is tagged and whether it is entering the appropriate priority queue. Bandwidth graphs and latency monitors may show congestion or jitter in high-priority queues, indicating a classification mismatch. Adjusting policy rules or retagging packets restores proper prioritization and resolves the associated performance impact. Network time synchronization problems extend beyond client devices and often involve the time servers themselves. If a time source drifts or becomes unreachable, clients may fall out of sync slowly over time. Using multiple sources and setting acceptable stratum thresholds allows for redundancy and ensures consistency. Peer trust settings prevent unauthorized time sources from affecting the clock. Polling intervals must be set to balance responsiveness with network efficiency. When properly configured, NTP ensures that system clocks match closely enough for secure token usage, accurate logs, and time-based automation to work reliably. Low-level network problems leave subtle clues in logs that may not immediately indicate the actual source of failure. For example, a log showing a failed connection with the message host unreachable could result from DNS misconfiguration, MTU mismatch, or VLAN blocking. Similarly, errors like clock skew or invalid token might point to time synchronization drift. Aggregating logs from DNS resolvers, proxy servers, overlay agents, and time services allows for a more complete picture of the environment. Cross-referencing timestamps and error messages supports root cause analysis when service behavior becomes unpredictable or intermittent. To maintain visibility into these low-level systems, cloud administrators must implement continuous monitoring and regular validation. DNS performance should be tested with synthetic checks, and configuration drift should be detected for all tagging and trunking rules. MTU should be monitored in environments with complex tunnels or overlays, and NTP should be audited for accuracy and resilience. Many issues in the cloud do not begin at the application layer. They begin in the network foundation. The Cloud Plus exam expects candidates to detect and resolve problems in these supporting systems as part of maintaining operational integrity. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.